Hello, my name is Florian Voigt. I'm with the Chair of Robotics, Science and Systems Intelligence of the Technical University of Munich, and I will present our paper called MultiLevel Structure versus End-to-End Learning in High-Performance Tactile Robotic Manipulation. First, a brief introduction is given, then our multi-level structure learning approach is shown, and based on this, the parameter space partitioning. Subsequently, our pack-and-hold experiment is presented, the results discussed, and a conclusion given. Learning robotic manipulation tasks using off-the-shelf deep reinforcement learning is time-consuming and requires lots of data. An alternative to this is using parameterizable compliant skills, which have the potential to accelerate learning. On the right, you can see the multi-level structure learning approach in comparison to standard deep reinforcement learning. The high-level learning layer of the multi-level structure employs an arbitrary learner to find optimized parameters. The learning layer sends proposed parameters to the semantic layer, which decides if parameters are feasible and, if executed, if these have been successful. Based on these parameters, the manipulation layer generates continuous commands, which are then applied via the control layer to the robot. On the left, you can see the resulting reduction of the potential solution space to a meaningful search space. Due to these layers, the constraints of this reduced search space are known, and the problem of finding optimized parameters for a given cost function becomes finding optimized tuples in a hypercube. For our parameter space partitioning algorithm, we make the following assumptions. The solution space in the previously mentioned hypercube is at least piecewise continuous in regard to a cost function we want to optimize. Also, this hypercube is separable by an arbitrary reward R separation into spaces which yield rewards above or equal to R separation, and spaces which yield rewards below R separation. This separation is in our case done via a support vector machine. The intuition of our algorithm is the following. Our algorithm consists of several episodes. For each episode, a fixed number of parameter tuples is sampled and then applied to the problem. In return, we get a reward. Initially, we sample over the whole search space. After each episode, R separation is calculated as the mean of the rewards of all successful trials. Based on this, we calculate the partitioning of the parameter space, which is then used in the next episode for sampling. Eventually, we converge to a useful parameter subspace. Here, a brief comparison of our algorithm to particle swarm optimization, genetic algorithm, and HiREPS based on two simulative benchmark problems with multiple dimensions is shown. A distinctive outperformance for all dimensions can be seen. In the following, we show our pack-and-hold experiment setup. In our experiment, we try to learn how to insert a key into a lock. We chose this task due to its difficulty and high complexity. The skill we're trying to optimize features 23 parameters. Our goal was to compare our structured learning approach to standard deep reinforcement learners. Therefore, we applied HiREPS, CMAS, and our PSP algorithm with the structured learning system, and for deep reinforcement learning, deep deterministic policy gradient, its twin-delayed version, and soft and asynchronous actor critic. All experiments were carried out using a compliant Franka Panda robot. For each learner, we carried out 10 experiments consisting of 200 trials each. All three parameter-based algorithms which were applied to our multi-structure learning approach found feasible solutions rather quickly. Also, all three of them converged to similar minimal cost. Eventually, we were able to execute the key and lock task successfully in around 0.3 seconds. None of the applied deep reinforcement learners was able to solve the problem within the given time. While all three parameter-based algorithms were able to solve the problem, both HiREPS and CMAS weren't able to propose working parameters reliably. In contrast to this, our partitioning algorithm shows an increasing ability to do so. Also, both HiREPS and CMAS tend to find unreliable solutions, which were prone to yielding far higher costs or even being unsuccessful. Such undesired results could be observed for our partitioning algorithm. In our paper, we extended the structure-based manipulation learning approach with our parameter space partitioning algorithm. Compared it to other algorithms in a simulative benchmark, it could show significantly higher performance. Then the combined system of algorithm and structure-based learning approach was applied to the key and lock task and outperformed several state-of-the-art deep reinforcement learners. In comparison with the other parameter-based algorithms, we could find interesting properties in regard to robustness and reliability. Thank you very much for your attention and have a nice day.